Hello, this video is about the topic of dynamic equilibrium, which appears on both GCSE and A-level chemistry. So for the AQA GCSE, you're looking at topic 4.6.2 and 4.10.4. Both of these are in paper 2. And for OCR's A-level chemistry, it's in topic 3.2.3, cunningly titled equilibrium. Right, so what we're dealing with when we have equilibrium is a special type of reaction which is reversible. And what that means is that instead of the standard reaction where reactants turn into products, these products can react together and reform the original reactants. So the one that is probably the most associated with this topic would be when we take a nitrogen and we take 3 hydrogens and we react them together and we form NH3, which is ammonia. Except the ammonias can react together and split apart and reform these elements, which can then react together and reform the ammonia. We get what's called dynamic equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. When the two rates are equal. And the key word for you here is rate. So the rate of the forward reaction is the same as that of the reverse reaction. And the reason this is of interest to us is because it will appear that the reaction has stopped because the concentrations of the reactants and the products will stay constant. Now the reaction hasn't stopped. It's just that for every single amount of reactants forming products, the exact same amount is returning back. So if you had, let's say, 40% of the stuff was existing as the reactants, 60% would therefore be existing as the products. Now it might be that every second 10% of the reactants are turning into products, but 10% are being reformed. So it looks like nothing is happening, but there is constant reaction, but the rates are the same. Okay, now there's a couple of key terms that you need to understand for this as well. The first is position of equilibrium. And this simply means how far to the left or to the right this equilibrium is. So I picked 40% here, but it can range from anywhere from absolutely tiny all the way up to 99.999. The next thing that you need to know is that if the question asks you about yield or percentage yield, then it's equilibrium that's going to be controlling this. So if we're trying to make a product, we want to make as much of it as possible. So we want a high percentage yield. So if you see the higher the percentage yield, that means there's a higher amount of products, and that means the equilibrium, or rather the position of equilibrium, is further to the right. Okay, next idea, Le Chatelier's principle. What this means is that if there's a system and it's in dynamic equilibrium, it will oppose any changes to the physical conditions. Now this is temperature, pressure, and the concentrations of either the reactants or the products. But the key thing for you to know is that any physical condition which is changed, well, that will be opposed. And I'm going to try and give you some actual examples of that just now, starting off with pressure. Here is the Haber process written out. If it's about pressure, the key thing you're looking for is all about the moles of gas. On the reactant side, there's no coefficient or big number, which means there's 1. 3 H2s, so that means there's altogether 4 moles of gas here. And on the product side, we've got 2 moles of gas. So if we increase pressure, the key thing, Le Chatelier's principle states, is that the position of equilibrium, that key phrase that I used earlier, position of equilibrium will shift to oppose this change. So what that means is it will look to decrease pressure. So every time if you get one of these questions, if the conditions are an increase in pressure, the equilibrium will decrease pressure. And to work out how that happens, you simply look at the equilibrium, you look for the side with fewer moles of gas. So here it will shift right as there are fewer moles of gas. And if you want to count them and show off, that always persuades the examiner that you are worthy of their marks. So you do to let them know that 2 moles is less than 4 moles. Okay, next condition, temperature. For this, everything you're looking at is whether something is exothermic or endothermic. They will give you the information, or you're 12, so you might have to calculate it, but you will be provided with enough information. For the Haber process, the forward reaction is exothermic. Year 12, delta H is negative. Year 11s, don't worry about that. So, going from left to right, it's exothermic, which means that it gives heat out. We know already that equilibrium opposes change, so I'm going to stick with increase because that's what we've done so far. If we increase temperature, equilibrium will try to decrease temperature. And that will happen every single time for any equilibrium. You increase the temperature, it will try to decrease the temperature. The way it does that is not by doing the exothermic, and the word they want you to use for this is favour. It will favour the endothermic reaction. Now here's where you've got to keep calm. It tells you the forward is exo, it doesn't say anything about endo, but if the forward reaction is exothermic, the reverse one must be endothermic. So this here, for our increase in temperature, the equilibrium will shift from right to left. So the equilibrium will shift left. Now, if we look up here, the yield that we were talking about was how much of the product. For this one, this would decrease yield. If we go back over to the pressure one, we increased pressure, equilibrium tries to decrease pressure, it shifts to the right because there are fewer moles of gas, so for this one it would increase yield. For both pressure and temperature, the reverse arguments hold true. So you could equally decrease pressure, and that would lead to a decrease in yield for this reaction. And for this reaction, you could decrease temperature, which would lead to an increase in yield. Okay, thank you very much for this. I'm going to do part 2 to this video shortly. Cheers.